Alright, so in this video we're talking about maximizing and minimizing functions. In particular, we're going to look for turning points and the local max and local min. So another important feature of polynomial functions is that they have turning points which correspond to local max and local min. The y-coordinate of a turning point is called a local maximum if the function is higher than all the other nearby points, and the y-coordinate of a turning point is a local minimum if it's the lower than all the other points that are near it. And we have a rule: the graph of every polynomial function of degree n, again, n is our highest power in our polynomial, has at most n minus 1 turning points. Also, a polynomial has n distinct real zeros, then its graph has exactly n minus 1 turning points. So, an important rule right here, you probably want to definitely highlight that. Kind of difficult to understand what it means, but hopefully it'll make sense. So in example 13, we want to graph the function x cubed minus 3x squared plus 2 and identify the x-intercepts and the points where the local maximum and local minimums occur. First off, our highest power n, so n equals 3. That means we're going to have at most n minus 1, in this case 3 minus 1 equals 2 turning points. Okay, so now let's actually graph this thing. So y equals, I'm just going to put this in y1. So I have x cubed minus 3x squared plus 2. Graph it. I'm going to zoom 6 so I'm starting a new picture. And I can see 1, 2 turning points. I start going up, but then it falls down, and I go up again. So there's 2 turning points. Also, I want to find the zeros. Okay, the zeros are essentially the x-intercepts. Zeros is a fancy name for x-intercept, and there's 3 options. So that's second count, option 5. First curve enter, second curve enter, yes. And now you notice nothing's happening when I do second curve. That's because I have nothing in y2. And that's what we're used to doing. So instead, to find the zeros, I'm going to hit second calc, option 2 for 0. Now the calculator is going to ask me something, left bound. So what you want to do is be on the left side of your turning point. So I'm looking at this turning point right here in the middle. Right bound, you want to be on the right side of your turning point. Enter. And then guess. You want to be on your turning point. And so my first 0 is negative 0.73, and again I'm rounding. So my zeros, x equals negative 0.73. That's one item. I want to find another one. I have it right here in the middle. So second calc, option 2 for 0. I want to be on the left side of my 0, the right side of my 0, and then guess somewhere there in the middle. X equals 1. And then my last 0 is over here on the right, so second calc, option 2 for 0. I want to be on the left side and on the right side, and then I want to go somewhere in the middle to get to the 0. So about 2.73. Okay, so let's look at our rule again. So we know there's at most 2 turning points, which we solved graphically, and we have 3 distinct zeros. Distinct just means 3 different zeros. None of them repeat. Well, let's go to the rule. Also, a polynomial has n distinct zeros, then its graph has exactly n minus 1 turning points. Here we have exactly 3 zeros, our highest power, n equals 3. So that means we had exactly 2 turning points. We could have had fewer, but we had exactly 2 because we had 3 distinct zeros. In example 14, you're designing an open box being made of a piece of cardboard that's 10 inches by 15 inches. The box is going to be formed by making cuts shown and folding the sides of the flap or square. You want the box to have the greatest possible volume. How long should you make the cuts? What's the maximum volume? What dimensions would the finished box be? Okay? So what we want to do is to first think about volume. So volume of the box is length times width times height. Alright, so first off, let's think about what we got. We have, if we fold this piece up, we know this piece is going to height is going to be x. from here to here is going to be 10 minus 2x. And I'm saying minus 2x because I'm folding that piece up. Okay, so that's going to be, if you imagine folding it, that's going to be standing on its end. So really it's not exactly 10. You're taking away x. I'm taking away x here. And then finally this last piece is going to be a similar idea. We have 15, but then we're taking out this square and this square. So 15 minus 2x. Now, it doesn't really matter what I call length, width, and height. That doesn't matter at all. But I'm just going to go ahead and call this one's obvious the height, the length, and the width. Okay? If you want to label yours a little bit different, that's fine, but you've got to have it besides the correct dimensions. So plugging in what I know, so I have length was 10 minus 2x. You have to have that in parentheses because there's more than one thing there. The width was 15 minus 2x. And then the height was x. That's my volume. Okay? What I want to do is the volume to have the greatest volume possible. Okay? So, when my x is changing, instead of y, my values for the volume are going to change. So what I want to do is graph this thing. So, instead of v equals, I'm thinking about y equals. So I have 10 minus 2x, and then 15 minus 2x, and then x there. And I want to graph this. Zoom 6 for a new picture. And now, it's not a very nice picture, so I'm going to zoom option 0 for zoom fit. And now what I'm going to do is I'm going to actually do a thing called zoom box. We've already used zoom box a few times, but I know that I'm looking at only, I want to draw a box essentially around nice pieces of my graph. So when you do zoom box, that's what the calculator lets you do. It just lets you focus in on the pieces of the graph that you're interested in. So I'm drawing my box right now. Once you have it, hit enter. And now I have a very nice picture. So what I want to do is pick a value of x from this graph that's going to maximize the volume. Now you've got to keep in mind the volume has to be a fixed number. You can't have a box with infinite volume. If you had a box with infinite volume, you could put everything in the universe in there. Well, as far as I know, no box like that exists. Also, your volume cannot be negative. It doesn't make sense for your box to be able to hold a negative amount of stuff. So you're looking at the part of the graph that's positive, but also has a limit on it. So on this find, here's my local maximum. Right here. That's about the point I want to try to find. And it's a maximum, so what I'm going to do is second count. Option 4 for maximum, and the calculator is going to ask you a few questions. First off, for left bound, you want your cursor to be somewhere on the left side of this hill. For the right bound, you want your cursor to be somewhere on the right side of the hill. And then for the maximum, you're going to move your cursor in position and hit guess. So my maximum is 1, it happens at x equals 1.96. Comma 132.03. Now, that's an ordered pair. We had x and y, x and v, okay? So, x and v. Kind of looks like an x there. Let's clean that up just a bit. So here, what this tells me, the x value tells me how far I need to cut into the box, so how long this incision needs to be. And what this number tells me, the v tells me how much stuff I can put in it. So that's the maximum volume. Okay? And we've answered both questions. What would the dimensions of the finished cut be? So we need to answer that. So what we're going to do now is use our x. So we know the height of the box is going to be 1.96. All I'm doing is plugging in my x values now to find the dimensions. Here I'm going to plug in, so I get 10 minus 2 times 1.96, which is going to be this calculator here. So I'm going to go to my main screen to do this. So 10 minus 2 times 1.96, I get 6.08. And then finally for this piece, this dimension, I'm going to plug in 15 minus 2 times 1.96. You you can use your calculator to help out. I get 11.08. So now we have all the dimensions of our box. We have our height, our length, and our width of our box. Okay, so, and that's the dimensions that's going to produce the approximate greatest volume. And that's it for this video. Let me know if you got questions. The local mins, local max, they show up in application problems like we just saw all the time. So be sure you understand it. Thanks.